This question comes from me. It's a new chapter from the 10th anniversary edition of What If, which is now available online and in print. At the end of the laser pointer video, we constructed an array of lasers with a total power of 2 × 10⁴ watts, which not only lit up the moon, but violently ejected it from orbit around the Earth. We decided that was enough power. But why? You can always make a number bigger. No one can stop you. There are infinitely many numbers, and I want to know, what if we tried even more power? A 2 × 10⁴ watt laser is powerful. When we turned ours on, it made the moon-facing surface of the Earth significantly more luminous than the sun. That's impressive, but we can do better. The universe contains death rays that make our moon-obliterating beam look like a handheld laser pointer. Gamma ray bursts. A gamma ray is just what we call a very high-energy photon of electromagnetic radiation. When you see a chart of the electromagnetic spectrum, gamma rays are basically anything more energetic than X-rays. At the high end, they're literally off the chart. They come from high-energy events like nuclear explosions. Gamma ray bursts are made when something very bad happens to a star. When massive stars collapse, their cores give in to the crushing pull of their own gravity, release an enormous burst of energy, and tear the star apart from the inside. For reasons that we don't fully understand, these explosions often produce jets shooting away along the poles of the collapsing star. These jets can travel across much of the universe, and when Earth is in line with one of them, we see it as a flash of gamma rays from deep space. We didn't know about gamma ray bursts until we launched a satellite to watch for gamma ray flashes from nuclear explosions on Earth, and we were surprised to see flashes coming from everywhere else in the universe instead. The peak power of beams from gamma ray bursts can be on the order of 10⁴ watts, which is much more powerful than our laser array. To get a 10⁴ watt death ray of our own, we'd need to give each person on the moon-facing side of the planet a 2 × 10⁴ watt laser. That is, each person would need a laser 10 billion times more powerful than the final combined laser that violently ejected the moon. This is an implausible scenario, and it wouldn't work for reasons we'll get to in a minute. But first, let's think about what we could do with a beam like that. We'd have to focus it carefully since laser beams spread out as they travel. The minimum angle of spread depends on the size of the source of the beam. For laser beams emitted by lenses 2 meters wide, the limit is about 0.1 arc seconds, or 3/100,000ths of a degree. The laser beam limit formula is weirdly similar to the formula used to determine the maximum resolution of telescopes like Hubble, because in a sense, a telescope is just a death ray running in reverse. Hubble has a 2.4 meter mirror, and its angular resolution is a little less than 0.1 arc seconds, similar to the angular limit of our 2 meter laser. The laser array from the original chapter was pretty powerful, but not particularly narrow. If it had been focused into a Hubble-style beam, it could conceivably have fried the surfaces of planets anywhere in our galaxy. A 10⁴ watt death ray would be much worse. If we tightly focused it down to the diffraction limit, it could reach targets far outside our galaxy, frying the surfaces of planets up to 5 or 10 billion light years away. But don't rush out to buy a 10⁴ watt laser just yet. At cosmic energy scales, normal optics breaks down. For example, if a beam is powerful enough, it could exert a gravitational pull on itself. Photons carry energy, and energy creates gravitational fields. For normal light beams, this is negligible, but for a 10⁴ watt laser the size of the Earth, photons on the outer edge would experience an acceleration of over 10 Gs toward the beam's center line. But physics has another surprise, one that finally puts an upper limit on how powerful lasers can get. Namely, if a beam of light gets too bright, space itself stops being transparent. If you pack enough laser energy into a small enough space, quantum mechanics predicts that the strong electromagnetic fields will result in spontaneous creation of particles and antiparticles. These particles, mostly electrons and positrons, would intercept some of the laser energy, which would result in more particles being created. For laser power densities above about 10⁻26 watts per square centimeter, this process is expected to cascade, fully halting the laser's progress and providing an upper limit on how much power our beam can have. In the end, it turns out physics is not math. You can always find a bigger number, but you can't always make a bigger laser.